Hello everyone. In this video, I would like to introduce our recent results on actively secure distributed point function and RAM-based secure two-party computation with up to 1-bit leakage. This is joint work with Xiaojie, Kang, Ruiyu, Yu, and Xiao. I'm Wenhao from Northwestern. So secure two-party computation is a fundamental case of secure multi-party computation, and it is a prevalent research area in applied cryptography. It means that there are two parties, for example, Alice and Bob. One holds secret inputs X and the other holds secret inputs Y. They want to jointly to compute a certain public function f and to obtain fxy without revealing any more information about their private inputs. So typical secure two-party computation protocols like Gobble circuits and GMW protocol consider the public function f as a Boolean or arithmetic circuit, and then evaluate the circuit gate by gate. In recent years, 2PC has been used in increasingly complex real-world applications. These include private database query, graph algorithms, stable matching, regular expression matching, and so on. In these scenarios, researchers have developed efficient 2PC protocols by combining the generic ways like Gobble circuits with custom protocols tailored to specific problems. One of the reasons that we need some custom protocol to build efficient 2PC for this application is that in those real-world applications, we need numerous random accesses, and these random accesses cannot be efficiently converted to compact circuits. Here, take stable matching as example. When we look at the code fragment of the Gale-Sharpley algorithm that is shown on the right, and especially when we focus on the highlighted sections, we can see that there are a lot of read or write operations on private positions. Thus, they need to design customer protocols to avoid the huge overhead occurring from converting a program to a circuit directly. But is there a generic way to handle all these kind of random accesses? Fortunately, the answer is yes. There is another model of 2PC called RAM-based 2PC. Under this model, protocols support both evaluation of circuits and random access of private data. Therefore, protocols under this model can be directly applied to those RAM program applications like stable matching. In the previous years, oblivious RAM is a classical way to solve the RAM-based 2PC problem. An oblivious RAM protocol allows a client to outsource storage of an array to the server, and then read from or write to that array without revealing to the server any more information about the data itself or the memory access pattern. A two-server ORAM protocol can be converted to a RAM-based 2PC protocol by letting two parties P0 and P1 to take the role of the server S0 and S1, and jointly emulate the client using, for example, Gobble circuit and the other secure two-party computation protocols. Recently, another line of work has been done to solve the RAM-based 2PC problem, and we name it DPF plus 2PC. It uses a distributed point function to convert a private index to the corresponding position in the memory, then design some customer protocols to achieve the whole RAM-based 2PC protocol. We noticed that even though DS17, which follows this new line of work, shows great efficiency with semi-honest security, it is still unknown how to efficiently to convert it to malicious security. Meanwhile, KY18, based on the classical way ORAM plus 2PC, is the only known protocol with malicious security. But KY18 shows a huge overhead to the semi-honest works, and this efficiency is not practical. We designed a super efficient protocol based on the DPF plus 2PC. It overcomes all barriers to malicious security with only up to 1-bit leakage. In the given experiment setting of 2 to the power 24 entries in the net setting, our work is more than 1,000 times better than QI18 and only need about twice the cost of the state-of-the-art semi-honest result like DI17. So we show a great efficiency of our work, and in the following slides, I will quickly show you our ideas and contributions, as well as the benchmark results. As our protocols closely follow this new line DPF plus 2PC, I would like to firstly introduce a very high-level idea of this scheme and take DI17 as an example. In that scheme, they use a first semi-honest secure DPF protocol and then semi-honest secure and reactive 2PC protocol as two building blocks. Then they design customer protocols of local operation collecting these two key building blocks to make a RAM-based 2PC protocol. And here is our design. We, based on the DS17 design and to achieve the overall malicious security of our protocol, we need to compile each component to be maliciously secure. So we design a new maliciously secure distributed point function protocol with up to 1 bit leakage. Then we extend the technique of dual execution and design a maliciously secure and reactive 2PC protocol, still with up to 1 bit leakage. Next, we extend local operations in DS17 to make it support authenticated sharing. And finally, we use random linear combination to batch all consistency checks together. We would like to mention that, firstly, our maliciously secure DPF protocol has a great improvement on the communication comparing to the prior maliciously secure DPF protocol with SAM leakage. What's more, our design is compatible with all the other building blocks, while it is still unknown how to efficiently to put the prior work to this to this scheme. And this part of results can also be a useful building block of two-server PIR, OLE extension, and so on. So it can be applied in many other scenarios. Also, we would like to mention that our maliciously secure and reactive 2PC protocol exactly has a twice cost overhead to the semi-honest garble circuits. So it is essentially the same as dual execution. And this reactive feature enables many other applications if we need to combine this GC with other protocols. And finally, you may think that there might be a lot of leakage since for each component we have up to 1 bit leakage. But indeed, our batched consistency check ensures that there is only 1 bit leakage during the whole execution of this RAM-based 2PC protocol. We benchmark the efficiency of our protocols along with DI17, VHG23, and KY18 by comparing the work clock time per access to the size of memory for each one in both network settings. Here we would like to mention that VHG23 is the state-of-the-art semi-honest secure RAM-based 2PC protocol in the one setting. And we can see that first, our protocol is competitive with both semi-honest protocols DS17 and VHG23 on both network settings. And our protocol consistently outperforms KY18 by at least 2 orders of magnitude in both NAN and WAN network setting. We can also see that random access in our protocol costs about 14 milliseconds, when the entry size is about 10 to the power of 6. And it shows a great practical efficiency in some real-world 2PC applications. Also, we analyze the cost breakdown of an access operation of our protocol in different scenarios. We divide access into 6 stages, and from the figure, we can conclude that the main cost in the net setting is local memory access when the memory size is somehow large, like more than 2 to the power 26. At the same time, the bandwidth and the latency limitation is the bottleneck of our protocol in the WAN setting. We conclude our talk with this summary. In this paper, we mainly design actively secure DPF as well as reactive and actively secure to PC protocols. And we use these 2 key building blocks to build an actively secure RAM-based 2PC protocol with up to 1 bit leakage and very high efficiency. If you are interested in any parts of our work, please check our paper online on ePrint, and you can scan the QR code here to get the paper. Thank you for your listening, and if you have any questions, you can always drop me an email.